Hi kids, welcome to UIL Science. I'm Paul Kennedy and today's problem is a harmonic motion problem. A 100-gram mass is attached to a spring hanging vertically. The mass is pulled by 15 centimeters from the equilibrium point released from rest. Harmonic motion ensues and the period of the motion is 1.35 seconds. What is the speed of the mass as it passes through the equilibrium point during the oscillation? Now, here's our spring. If we extend it down 15 centimeters and let it go, it sits and bounces up and down. Now when it's just hanging here, this point right here is 15 centimeters, or no, is the equilibrium point, or just hanging. And when this is bouncing, that's its maximum speed right there. The spring's not pushing or pulling against it. And so we want to know how fast it's moving at that point. The period, which in this case is equal to 1.35 seconds, is defined as t equals 2 pi times the square root of the mass divided by k. K is the spring constant. So let's solve for k. So in this case, we square both sides, so we get t squared is equal to 4 pi squared times the mass, all divided by k. And if we switch it around, we can bring the spring constant out and say that 4 pi squared times the mass over t squared is our answer. If we put in all of our numbers, 4 pi squared times 0.1 kilogram, we want to put it in standard units, divided by 1.35 seconds, and we square it, we come up with the period as being 2.17 kilograms per second squared. Now that's kind of weird units, but if we multiply instead by meters, top and bottom, meters over meters, or this magic power 1, we end up being able to transform the units to 2.17 newtons per meter, which is something we can deal with. Now, the energy of a spring is defined as E equals 1/2 Ka squared, where A is the amplitude and K is a spring constant. So if we sit there, and that's how strong the spring is. So if we take and we put our numbers in here, our spring constant, 2.17 newtons per meter, and we take and we multiply by our amplitude, which is 0.15 meters, and we square it, we come up with 0.0244 joules. Now, something interesting here. Remember, energy is conserved. At this point, the spring is not pulling or pushing. There is no, this is all velocity at this point. So we can take and say that that energy can also be related to mv squared, 1/2 mv squared, because it's going through the equilibrium point. So if we take and solve for v, v squared is equal to 2e times m, and then we square root that. V is equal to the square root of 2em. We end up with this being, 2e divided by m. 2e divided by m. I made a mistake. Always be willing to come back and correct your mistakes. And when we shove it back in there, we end up with the velocity being 0.698 meters per second. Now, originally we were given units in grams and centimeters, so we need to convert this back. And to convert that back, there's 100 centimeters in a meter, and we end up with 69.8 centimeters per second. I do want to take one moment to notice when I did this, I kept my numbers out of the equation until I came down to the point where I needed to get a calculated number. That makes it a lot simpler. I'm just dealing with symbols up until then. I'm not dealing with having to carry numbers and decimal places around. And as you notice, the answer comes out 69.8 centimeters, which happens to be answer D. Thank you.